practice problems at the end of the 1.2 note package about radicals and rational exponents. Okay. So when we're working with radicals, I always think the best thing to start with is to start by just writing out your perfect squares. I like to write them in the margin here. So my perfect squares are 1 times 1 is 1, 2 times 2 is 4. You can scrub through this, obviously, if you know all your perfect squares already. But when I was learning my perfect squares and doing a lot of square rooting, I used to like to just write them out so they're easy for me to just see and recognize. And if I was really still learning them, I might even add a little bit more. I might actually just write down this is 1 times 1, and that's 2 times 2, and so on, and until you got to 12 by 12. Dot, dot, dot. Now, we've also got some cube roots, it looks like, a little bit later. So maybe I'll write down my perfect cubes as well. But those might be new for some of us, so I'm actually going to write them out as, oops, that pen is done. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. And 5 times 5 times 5 is 125. And I like to usually stop at those two, 12 times 12 and 5 times 5. You can keep going, of course. All right, so next, let's dig into the question. So the question asks us to circle 3 radicals that can't be simplified. And we're also going to simplify the rest. And we're going to try to do that without a calculator. We're going to try that just with the aid of our perfect squares and our perfect cubes and some tenacity. Okay, let's see how we do. All right, so they start out pretty straightforward. This one really just asks, do you know what the symbol means? Right? It means I'm looking for 2 numbers that are the same that multiply to 81. Another way to think of that is I'm looking for a number that if I square it, gives me 81. And 81 is a number in my list of perfect squares. It's 9 times 9. And so that means root 81 is just 9. Root 1 is just another straightforward square root. It's asking what number when I square it gives me 1. And the answer is 1. Okay, this is a 2-step question. It's 14 multiplied by what the square root of 1 is, which is 1. And so then I have a multiplication step. Okay, now I just did 2 steps there, and you should know that as we covered a little earlier in the week, all radicals can be written as exponents. So when you're evaluating a radical, there's actually an exponent step in BEDMAS. So we evaluate our exponents, which is going to include our radicals, before we do our multiplications. All right. This is a pretty similar style question, 2 steps. I've got -7 times the square root of 0. Now, I didn't actually list 0 in my list of perfect squares, but technically it lives right at the top. The first perfect square is 0 times 0 is 0. It's also the first perfect cube, and so on. So 7 times 0, that's just 0, because anything times 0 is just 0. Okay. So we're going to keep going here. So we've got 2 times the square root of 4. That's just 2, so we're going to get 4 there. I'm going to try to go a little quicker through these because I think a lot of these people are going to be pretty comfortable with. 5 times square root of 169. So I'm going to look down here and say, well, my perfect square list doesn't go as high as this number. So is it a perfect square or isn't it? So we might take a second to just try the next set of numbers. We've got 12 times 12, so it's 13 times 13. And it's okay not to know that, but it is important that we remember how to multiply things if we need to. We multiply this 3 by 3 and get 9, and 3 by this 1, I get a 3. Then I'm going to move over to this 1, but that's in the tens place, so I add a 0 here. I'm going to multiply my 1 by 3 and get 3, and my 1 by 1 to get 1. And then I'm going to add these together. 9, 6, 1. Okay. Now it looks like 169 is actually 13 13ths. So that means the square root of 169 is actually just 13. And so then I have 5 13ths. And you can take a second to multiply those through. And eventually we'll get 65. Okay. Now there's a little trick for multiplying by 5. I just take half of 13, which is 6.5. And I just shift the decimal place over 1. So it gives me 65. Okay. 3 root 10. Okay, so I've got 3 times, well, it looks like 10 is not a number in my list of perfect squares. So this can't be simplified. So this is one of the hidden radicals that we can't simplify. So I'm going to circle that in blue. All right. So this one says it's just a square root of some number squared. Okay. Well, I might ask what times itself gives me x squared. Well, that's x, isn't it? Yeah, x times x is x squared. And these are inverse operations. Well, actually, there's a little bit more to the story, which we'll get to later. But we can, for now, we can think of them being inverse operations. So if you see a square root and a square, they like cancel each other out. It's like dividing by 2 and then multiplying by 2. And when we do algebra, they kind of undo each other. Okay. Moving on, so we got these 2 numbers here that multiply together to give us 9r squared. And I feel like maybe I'm zoomed out a little far. I'm going to zoom in a bit, and then I'm going to refocus to help see what's going on here. Okay, so here I've got 2 things. I've got a coefficient, 2 numbers that multiply together give 9. So it's a 3 and a 3. And then I've got 2 numbers that multiply to give me r squared. 2 letters, I suppose, 2 variables. It's going to be r and r. So the answer is just 3r. Okay. So here we've got the square root of negative 4. All right, so negative 4 isn't a number in my list of perfect squares. Actually, we stop at 0. Could we have gone lower? Are the negatives fair play? Let's think about that for a second. What 2 numbers multiplied together give negative 4? Well, you want to say maybe 2 and 2, but those are, so 2 times 2 gives us positive 4. But we want a negative, so maybe we'll make them, imagine what it is if they're both negative. Negative 2 times negative 2. But 2 negatives multiplied together give us a positive. 2 negatives also give us positive 4. So there's no 2 numbers that multiply to give us negative 4. Now, what I said isn't technically true. Matthew mentioned imaginary numbers in class today. A better word is a complex number. But there is an answer to this question. But it's not what we call a real number. It doesn't live on the number line. It has its own number line. So this does have an answer, but not in pre-calculus 11. So we're going to circle that as something that can't be simplified. All right. Moving on. Well, this question is kind of a variation on question I. We have 2 numbers, they're going to be the same, and they multiply together to get 49 m raised to a power 6. So we got, 49 is, oops, that's on our list of perfect squares, that's 7 sevenths. So I have a grandma candy in my mouth, so excuse me if my speech gets a little jumbled. And I've got some power of m. That must be here too. m to the power something gives m raised to a power 6. And the question is, well, what do I put here? And so I might just try some numbers. So 1 doesn't work because when I multiply, I add the exponents, m plus m, to get m squared. So that's not right. M squared and m squared, well, that would give us, when you add those, give us m to the power 4. So actually it's going to be m cubed. And when I multiply these together, I multiply the coefficients. 7 and 7 is 49. M cubed and m cubed, I add the exponents to get 6. So the answer is 7m cubed. Okay. So roots can often be challenging when we come to having fractions, and sometimes they act in a little bit of a counterintuitive manner. So we need to think what times itself gives us 1 over 4. Well, they're going to have to be fractions, aren't they? Something over something and something over something. Otherwise, we're not going to get a fraction. And so we might need to remember how do we work with fractions? How do we multiply them? Well, multiplying them is just the numbers multiplied across the top. So it's going to be 1 times 1. And that gives us 1. And the numbers on the bottom just multiply together to get this denominator. So it's going to be 2 times 2. So root a quarter is just a half. And that's weird because a half is bigger than a quarter. Usually when you take a square root, it actually gives you a number that's smaller. But actually, when you have numbers smaller than 1, they actually give you bigger numbers. Now, there is another option. So instead, we can think of it this way. I can rewrite this square root as the square root of 1 over the square root of 4. Because that's the same thing, just a different way of writing it. And then I can just solve it simply by saying it's 1 over square root of 4 is 2. So either way, we get a half. All right, let's see if we can use those skills to solve this problem. Okay, so we've got a multiplier in front. So it's a 2 times. And we're looking for two things. I'll write those over to the side that multiply together to get 4/9. Right? All right, so 4 is a perfect square. That's 2 2s, so it's 2 times 2. And 9 is also a perfect square. It's 3 times 3. So overall, this whole radical can be rewritten as just 2/3. All right. Now then we're going to rewrite that as a multiplication statement, which, I mean, it is, but I'm going to set it up so we're multiplying fractions. 2 can be written as the fraction 2 over 1 times 2 over 3. So then we'll multiply across, and we'll get 4 on the top, and 1 times 3 is 3 on the bottom. Okay. So that's halfway through the alphabet. So we'll try and speed it up for the rest here. Looks like some of them don't look so bad. All right. So I'll use blue here so I don't get the answer confused. Got a negative. Give me 1 second here. I've had some trouble with the video lately. And I want to make sure I'm not wasting my time by recording this and then having it glitch out like it did last time. Well, it looks safe. Okay, so I'm going to continue. All right. So I'm going to use a different method to solve this one. I used just the regular root habit of just finding two things that multiply together to get us 4/9 for question M. But for L, we use two different methods, and I'm going to use the second one this time. I'm going to rewrite this question as negative root m squared over root n to the power 4. Okay. So I'm going to keep that negative in front. Say, okay, root m squared, well, that's really similar to question H, right? Just a different letter. So that's just going to become m. And the root of n raised to an exponent of 4, well, that's going to be n squared. N squared times n squared gives us n to the power 4. All right, moving on. Cube root of 0. Well, we said earlier that 0 times 0 is 0. Pardon me, 0 times 0 times 0 is 0. So that means the cube root of 0 is just simply 0. Simple as that. Not a trick question. Now, we also talk about how a square root of a square, well, those kind of undo each other. They're inverses. And that's the same with cube root and cubing. They just cancel out. However, if we weren't sure about that, we could always prove it by considering what value can I multiply by itself 3 times to get y cubed. And the answer is just y, right? Y to the power 1. And I would add those exponents each time to get 3. So the answer here is just y, which you can also think of as being something you get when you cancel these guys out. We just left with a y. All right. Now we've got the cube root of negative 1. Now, we saw earlier why we can't have the square root of a negative. However, can we have a cube root of a negative? And the answer is actually that we can. That when we have 3 things that we're multiplying together to get a negative value, and they're the same, as long as they're all negative, well, that's going to work out. We're going to get a negative number because 2 negatives multiplied together make a positive, and then multiply that by another negative to get a negative. All right, so we're going to, and lastly, we want to say, well, what do we need to get 1? Well, it's going to be negative 1, and negative 1. So the answer is just negative 1. And that's allowed with cube roots and really any radical with an odd index, because we have an odd number of negatives, which allows us to get a negative out of it. Okay, so this is just a negative answer of whatever the cube root of 27 is, and it looks like 3 times 3 times 3 is 27. So we're going to say the cube root of 27 is just 3, and we've taken the negative version of that, so we're going to get negative 3. All right, so we've got negative 3 here, and it's going to be multiplied by whatever the cube root of negative 64 is. Okay, so that's going to be, well, the cube root of 64, is 4. So the cube root of negative 64, that's going to be negative 4 times negative 4 times negative 4. And that'll give us, if we crunch the numbers, negative 4 times negative 4 is 16, times a negative 4, well, that's going to be negative 64. Okay, good. Pardon me, I got a little distracted there. Okay, so now I've got negative 3 times negative 4, and we can simplify that. 2 negatives multiplied together make a positive, and 3 fours is 12. So we're done. Okay. Let's continue along here. Now, sometimes notation can get a little funky here. Does that say x cubed, or does that say the cube root? And I'm looking, and I think I'm going to use my judgment. I feel like I can draw a vertical line that separates them. So that's negative 4x times the cube root of 125x cubed. All right, so we'll come back to the negative 4x, but I'll ask, well, what do I multiply by itself 3 times to get 125x cubed? Well, I know I can multiply 5 times 5 times 5 to get 125. So we're going to get 5s here as coefficients. Now the question is, well, what do I multiply by to get this x cubed? Well, it's going to be pretty straightforward. It's going to be x times x times x. So overall, that whole expression becomes 5x. So I'm just going to rewrite that whole line, but instead of the big cube root, I'm just going to write what it all evaluates to. That whole thing becomes 5x. So overall, we're going to get negative 20x squared, because we have invisible ones there that add together, right? Okay. Now, as we addressed in class today, or pardon me, Thursday, there was a kind of a snafu with the printing, and I actually called this question 2 accidentally. It kind of automatically turned that into a 2, but I actually wanted to be a continuation of the first question. And that only makes sense because we were looking for 3 radicals that couldn't be simplified, and we identified 2 on the front page, but that was it. So there's a third one in this batch, and I do recognize that might have been a little confusing, so I apologize if you found that challenging. Now, so let's just, okay, so here we've got a 5th root. We'll continue along here. So that means we've got something multiplied by itself 5 times. And overall, it's going to give us the value negative r raised to an exponent 5. Well, that's pretty straightforward, isn't it? Because I'm multiplying it by itself 5 times. It's got to be negative r, right? Because so like the definition of what being raised to a power of 5 means, it's really itself multiplied by itself, multiplied by itself, by itself, and by itself. Okay, so the answer really is just negative r. Okay. Now we've got a 4th root of 125. Okay, so what's our strategy here? Should we be writing down all of the different perfect, squares, perfect cubes, perfect powers of 4? Well, I don't know, man. Maybe. Let's take a look. So if we come to a radical, we want to evaluate it. Maybe we're not sure if we can evaluate it. What we can do is we can do a little exploring, right? Oh, wait, we can save some time. Because this is an even index. I didn't notice that at all. I almost missed that. So what we're really looking for is 4 numbers that multiply together to give negative 625. Now, all those numbers have to be the same, right? That's the game we're playing. But let's think about this for a second. If they're negative, well, I'm going to get 2 negatives that give me a positive, and 2 negatives give me a positive. So overall, that's 2 positives multiplied together, and I can't get that negative value. If they're all positive numbers, we still can't get that negative value. This is no good because we have an even index. This cannot be simplified. Now, it actually can. We can use complex numbers to, simplify that a little bit, but not in pre-calc 11. Okay, let's move on. Here we've got the 543rd root of 1. So that means something multiplied by itself 543 times, and overall we're going to get it 1. So that means there's 543 terms in this expression. Okay, but I mean, maybe this is obvious to you. Like, there's only really one number that would work. It really doesn't matter if it's 543 times or a trillion times. It's number 1. 1 times itself, 543 times, gives us 1. So that's just 1. Maybe you think that is a trick question. I don't really think I would put it in that category. It's maybe deceptively simple. Okay. So next we're going to do a cube root of 125 over 64. So that means there's 3 fractions. They're going to multiply together to give me 125 over 64. So there's three numbers that multiply on the top to give me 125. And there's three numbers on the bottom. They're going to multiply together to give me 64. Now I already know that 5 times 5 times 5 is 125. So it's 5 times 5 times 5. And I already know 4 times 4 times 4 is 64 because I wrote all these out. So overall, that's 5/4. And I saw somebody in class today take a fraction like this and write it as a mixed fraction, which is 1 1/4, for example. But really, we are mostly interested in improper fractions. By the time we get to pre-calculus 11, this is useful for being able to place this term on a number line. But other than that, we can't do like a lot with it. We always need to turn our fractions into improper fractions to do anything with it. So this is actually a preferred form of fractions from now on. Okay, let's wrap up these two. So we know that we've already found three radicals that can't be simplified. So these guys are all fair game. Okay, so I'm going to address a 6 in a second. And again, it kind of looks like maybe 6 cubed, but I think it actually might be a cube root. So it'll be cube root of this negative thing. Okay, so we've got, I'm just going to cross out what I wrote there. I don't know why I wrote that. So we've got three things multiplied together. And they're going to give us negative 27x cubed over 216. So I know that these have to be negative numbers. And when I multiply three negatives together, I'm going to get a negative value. I also know they're all going to be fractions. Okay, so I'm trying to write those a little longer so we can see that they're fractions. Okay, now let's start with 27x cubed. What times itself gives us 27? Well, I might just check here. I can see 3, that's going to give us 27. So we're going to get a 3 on the top. And also we need an x on the top, so we're going to have an x there. And actually that would be sufficient. We don't need any higher powers of x's, because x times x times x is the definition of x cubed. And on the bottom, we don't really have any perfect squares written, perfect cubes written that go as high as 216. So what I might do is, because these guys get big pretty quick, is I might just ask myself, what is the next one? Well, I know 6 sixes is 36. And we're going to multiply that value by 6. And the question is, does that give us 216? If it does, well, this could be a perfect cube. If not, then it can't be simplified. So I'm just going to take a second, 36 times 6, and multiply them together, so I get 36. And 6 times 3 is 18, and I add the 3, so it gives me 21. Hey, look at that. It's 216. Great. So that means on the bottom, I've got 6 times 6 times 6. Oh, interesting. I see now that actually we could have simplified these guys from the start because they're both divisible by 3. They have 3 as a factor. So we could have made the whole question simpler. But we didn't because, well, I didn't see that. Maybe you did. All right, so we know this whole thing, the whole cube root is actually just negative 3x over 6. So I'm going to rewrite it. 6 times negative 3x over 6. Now I'm going to do two things here. I was about to simplify this fraction, but I can actually see that writing this out as a multiplication times negative 3x over 6, I can see that I can simplify diagonally by multiplying these guys across. Remember this trick from grade 9 maybe? You see a factor that's common diagonally and they're the same. I can divide these guys both by 6 to leave 1 and 1. So actually that just becomes 1 over 1 times negative 3x over 1. So that's really just a complicated way of saying negative 3x. Okay. Last question. So, okay, we talked about how we can distribute like a square root of a fraction onto the top and the bottom. So can you do that with a cube root? Yeah, sure, you can do it with any root, actually. So we're going to go a different route this time, just to demonstrate that we can solve it both ways. You don't have to solve it this way. So I'm going to distribute that cube root onto the top. I get a to the power 9. We're going to look for the cube root of that. And on the bottom, we're going to get the cube root of b cubed c raised to an exponent 6. Okay. Well, I'm going to break that into 2 steps. First, I'm going to say what times itself is going to give me a raised to an exponent 9. And next, with a different color, I'm going to say what times itself is going to give me b cubed c raised to an exponent 6. All right, well, I know I'm going to have a's for each of these expressions. And, well, I might just try some exponents. Well, 1 doesn't work. That's not high enough. 2 doesn't work because it'll be 2 plus 2 plus 2, which will be 6. 3 is going to work because 3 plus 3 plus 3 is 9. And kind of same thing here. I know I'm going to have a b and a c. And the b's multiply together. B times b times b gives us b cubed. So we're good there. But we're going to need a higher power of c. And if you try 2, for example, you're going to find that 2 plus 2 plus 2 is 6. Okay. So this whole thing can really be rewritten as a cubed over b cubed. Nope. Pardon me. Over b c squared. Okay. So we'll move on to question 2. So question 2 asks us to identify the index, which I'm going to highlight with yellow, the radicand, which I'll highlight with pink, and the coefficient, which I'll use a green highlighter for. Okay, so really this is just a vocabulary question. So an index, that's a number that's kind of like tucked in the middle here. And that tells us how many terms we're multiplying together to get the number on the inside. And so the index is 3 in this case. This is a cube root. The index of a cube root is 3. Now the radicand is another word for like the argument, the value on the inside of the radical. What is being cube rooted? That's the radicand. Okay. And that's going to be just -8. And in this case, we have a coefficient as well. We don't always have an obvious one. And so that coefficient is just 2 as a multiplier in front. Okay. So we're going to continue along. So we've got an index here. We've got a radicand, which I'll highlight in pink. And the coefficient is a number in front, but I don't see one here. But what we need to remember is that there's always an invisible 1 multiplied in front. So I'm going to list the multiplier as a 1. So the index is 5, the radicand is 243, and the coefficient, the thing multiplied in front, is a 1. Now, some people might say there's no coefficient, and I mean, that is really, we're just talking about a different way of looking at it at this stage. Okay. Lastly, okay, index. Is there no index for this? Well, we did talk in the notes about how the index of a square root is 2, but it's not typically written. So anytime you see a square root, we know the index is a little hidden 2. So the index is 2 in this case. The radicand, the value on the inside, is 25, and the coefficient is that multiplier of 6. Okay. How are we doing here? All right, well, I think we'll call this video here and come back and do the rest in a second.